wait a few minutes until more people.
Okay, we can.
Okay, so welcome everyone to the last session of talks of the Beyond IID. So I think we have a great session ahead of us. I apologize if there is some noise in my background because I had some problems this morning with the flight, so I'm at your airport right now. But anyways, it's a pleasure to have Gautam and Boris from the Wigner Institute to talk about super exponential distinguishability of correlated quantum states. So Gautam, please, the floor is yours.
Thanks a lot, Daniel, and thanks a lot, Masahito and the SASTEC team for organizing this Beyond IID workshop. And indeed, I'm going to talk about this topic, the super exponential distinguishability of correlated quantum states. And we have an archive paper for those with the same title for those who are interested in the details. And this work was done together with Milan Mosonyi, who is, I think, here, and two of his PhD students, Gergely Bunt and Gábor Maróti. And they are from the Budapest Technical University. And yeah, myself, I'm from Wigner. So let's start with the main topic. Oh, sorry, something happened with my, okay, I will not touch it. So basically, I'm going to talk about the hypothesis testing more precisely binary state discrimination, although we will also talk about like state discrimination that goes beyond binary a little bit. And of course, this is like a very, very, very standard topic within quantum information theory. Like the most treated case is, of course, the IID state discrimination, where we are presented like with identical prepared quantum systems, either identically prepared n times rho, so we have rho tensor rho n times, or sigma. We have this hypothesis, and one is the null hypothesis, the other is the alternative hypothesis. And then the task is to guess, given a state, which hypothesis is correct. And of course, we can choose a two-outcome measurement, and which will two-outcome POVM, basically, which will determine what we will choose. And for this, oh, sorry, do you hear me now? I had some net problem.
Yes.
Yes, I can hear you.
But
Sorry for this.
Please share your screen. Can you please share your screen again? I think the screen is gone.
Yes, of course. I'm sorry for this technical problem. My net is not the best. Okay, so so we have this, just to repeat a little bit, we are in this binary state discrimination scenario with the IID states, so rho tensor n and sigma tensor n. And then the task is to choose a POVM such that the outcomes will be like that we make errors when reading of the outcome is small. I mean, what are the error types? Like there are the type 1 error, which is like that we say that the the null hypothesis is we reject it. We say that it's not the raw tensor n, although in reality it was that. And of course, the probability of that is given by this simple equation shown here. And type 2 error, when we accept the null hypothesis, H0, although it's false, and then it's given by this, also this sigma tensor n. So this picture shows this these two scenarios, okay? And this is, of course, very well known, and it has been in quantum information theory, like really well investigated, what are the asymptotics of these errors. And in general, except for a trivial case, which I will talk about, the best achievable asymptotics is an exponential decrease to 0 for both of these error probabilities. And of course, there are many theorems regarding it, in like how we want to treat it. If we want to have if we allow for a finite error for one of the exponent, then the relative entropy gives you the exponent of the exponential decrease of the other error. And if you have a symmetric case, then you also have this type of exponential decrease. And I mean, this is a really long topic, and many things are very standard, and many things are known. And there is only this trivial case, which is not about the exponential decrease when rho and sigma are orthogonal. So, okay, so this is the IID scenario, but of course this workshop is called Beyond IID. So let's go do state discrimination beyond IID. Okay, so I mean, natural scenario would be to consider states which are not anymore of the form like rho tensor n or sigma tensor n, but are states that are, we take an infinite spin chain, rho 0 and rho 1, and we restrict those states to n spins and consecutive to an n part of the spin chain, and then make a POVM there. And actually, this has been also studied in the literature already, and the results that have been obtained here in this non-IID or correlated case is also usually showing an exponential decay of the error probabilities of both type 1 and type 2 errors. And for example, a nice theorem also due to Milan and his co-workers is that if you have a translation invariant local Hamiltonian and you consider thermal states for that one, then those actually this type 1 and type 2 error probability decrease also exponentially to 0. But there are also other families of state where this happens. So our question was, when we were looking at this topic, was that, I mean, the question was that, okay, so in such a correlated scenario in general, can a qualitatively different behavior occur for the type 1 and type error? Like how the asymptotics of those compared to the usual IID case. Okay, but moreover, of course, this is like maybe we can come up with some weird example which has qualitatively different. So maybe some example also motivated by physics. Of course, local Hamiltonians are always a good example which is motivated by physics. And we have seen, as I mentioned, that thermal states of local Hamiltonians, for that the error exponents are again decaying exponentially only. And actually, what else is left? Well, the ground state. So it would be nice to know that for ground states of local Hamiltonians, can a qualitatively different behavior occur for the asymptotics of the type 1 and type 2 errors than in the IID case. And actually, we answer both questions, and our answer is yes. Actually, there is a possibility we give a particular set of states where the type 1 and type 2 errors have a different behavior, and I'm going to show some theorems around that. And also, actually, those states can arise as ground state or of two distinct Hamiltonians. And then you can make a super exponential state discrimination. So I give away our results in a short term, but let's go a little bit deeper into this. So the particular setup that we are considering is actually a setup that originates from fermions, so from Car algebras, canonical anti-commutation relation algebras, and actually quasi-free states on these algebras, which are states that we have a very good handle on and that we can consider that we can work with well. And I mean, of course, it's very technical, the setup that we will consider. So I'm just gonna put up some part of description of this, but but that's technical. Like I'm just gonna explain a little bit about this. So basically, here is a piece of text which I will explain. So basically, what we are considering is a fermionic chain. So this is the Car algebra belonging to the line, so to the one particle Hilbert space L2Z. And actually, it's very interesting that translation invariant states, more precisely translation invariant even states, can be translated can be actually translated to the spin chain language. So we can move them and build up a translation invariant state on the spin chain. It's done actually, well, usually physicists talk about this Jordan-Wigner transformation, which makes this, but this only works for finite spin chains. But for an infinite spin chain, there is a little bit more complicated way of doing this. This translation, which is like a generalization of the Jordan-Wigner transformation due to Arak. And okay, so when we have such an infinite state on either the fermionic chain or the spin chain, usually these are defined by expectation values of the local and quasi-local algebras, okay, of the Car algebra or the spin chain algebra, and this is so also with the quasi-free states. So basically, if we have on the one particle space of the Car algebra a positive semi-definite operator Q, which we call usually symbol, then we can define a quasi-free state using this Q in the following way, that we have for each vector in the one particle Hilbert space, we can define in the Car algebra creation and annihilation operator, and actually monomials of this creation and annihilation algebra, creation and annihilation operators, they generate a dense subset in this algebra. And of course, this means that if I can now define a state, if I give expectation values to these operators that are consistent, and one way of doing it is actually to defining these expectation values as determinants corresponding to this Q operator in this form. Okay, and if Q is a translation invariant, then actually our state will be translation invariant, both on the fermion chain and then when we translate it to the spin chain. And in that case, all these translation invariant Q symbols can simultaneously diagonalize by the Fourier transform, which we define first in the one particle Hilbert space of the L2Z, and then can also be transferred to the full Car algebra. And actually then it turns out that every translation invariant symbol Q arises as an inverse Fourier transform of a multiplication operator, multiplication by some function on this L2 0 to pi subspace. Of course, where the function should be on 0 to pi, and it should be almost everywhere between 0 and 1, such that the it will satisfy that Q is between actually the zero operator and the identity operator. And in the case when we are talking about pure states, for example, ground state of certain operators, then Q will be almost everywhere, like this MQ function or the small q function. Its multiplication will be multiplying with a function that is almost everywhere 0 or 1. Okay, so basically it means that it's a characteristic function, and the pure translation invariant quasi-free states that are also number conserving, they are in one-to-one relationship with functions on 0 to pi that are characteristic functions. Okay, and this is this complicated setup, but just be with me, like I'm gonna give you the result and then interpret it in a physical term later. So basically, our main result is, and this we stated in a big generality, namely not in a binary, but actually in a multi, in a composite hypothesis testing way, is that suppose that we would have a set of quasi-free states, and these functions would be such that these qi functions belonging to one of the set of quasi-free functions states, and ri to the other set of translation invariant quasi-free functions would be such that there would be an interval mu such that qi would be 0 on this interval and rj's would be identities. Then actually yes, so then what we would have is actually something we would have it would turn out that we could do super exponential distinguishability between those two set of states. Okay, I mean, of course, if it's easier to think about just two states, one belonging to an interval, let's say 0, a, the other belonging to b, 2 pi, and a is smaller than b, then of course there is this then of course we can find that nu is for example 0 or a or 1 or b, 2 pi would play this role of the mu interval. And moreover we also show that actually this super exponential distinguishability is at least such that it goes e to the minus n log n. So basically, this means that the error exponents are actually bounded by like a minus c log n growth. So actually, it grows like e to the minus n log n, or faster. How the errors go to 0, and okay, and to make a physical example of this, like these were like very abstract theorems, we could consider a Hamiltonian, which is this Hamiltonian that I'm showing. It's a simple XX Hamiltonian with a transverse magnetic field H. And it turns out that actually the ground state of these Hamiltonians are exactly, or in the infinite spin chain, are exactly type of ground states which can be obtained from the fermion, from a quasi-free fermionic chain via this Araki-Jordan-Wigner transformation, and they belong to very easy. I mean, then they have, of course, a symbol Q, and as we discussed that that if it's a translation invariant state, which it is, then the symbol Q is nothing else than the Fourier transform of a multiplication operator by a function, and this function will be just simply an interval. And how big this interval is depends on the magnetic field. And just applying this theorem, we could actually make a corollary which shows that if we consider ground states, any ground states, for example, which have which belong to a magnetic field that is below, let's say, a value 80, and then other ground states that belong to this Hamiltonian, with the magnetic field which are bigger than, let's say, an H1, and H1 is strictly bigger than H0, then we could distinguish any of those these two set of ground states actually super exponentially. We were even able to give the operators that actually gives this super exponential error scaling. I mean the POVMs that gives you the super exponential error scaling, and this is actually how we prove the theorems. So basically, in a physicist language, what you have when you are talking about when you are talking about these functions that define the Q operator, they are like the so-called it's in a quasi-momentum space, and they are the field modes. And then what we are doing is that somehow we are mimicking in a finite system the Fourier transform. We are doing a discrete Fourier transform, and we are looking at n spins, and actually sort of like building projections like these POVMs out of that. That's how we proved it. But the main result is that yes, we have easy examples for Hamiltonians and generic states where we have super exponential discrimination between the states when we are correlated. So actually, I have only 2-3 minutes left. So I would just conclude and give an outlook. So I mean, the conclusion was, of course, that these two scenarios, what I'm depicting here, that the IID case and the non-IID case we show that it can be qualitatively different. And I think we are the first one who came up with such strict theorems on that. And also we came up with physical relevant examples when this happens. And I mean, this is just the start of this line of research. Now we want to understand whether it also has some physical, whether there are some interesting physics behind this, or whether we can connect it more to many-body physics. I mean, one particular case that we believe could be true is that if there is a phase transition going on, let's say in a Ising chain, then you can maybe distinguish super exponentially the critical point from, let's say, some points that are non-critical, or maybe even two states in the two phases in this phase transition. For example, in the transverse field Ising model, which actually belongs to those ground states belong to. They are also quasi-free states and translation invariant, but they are not number conserving. So it's not exactly what we are treating, but we hope to be able to also move in that direction. So thank you very much. I don't know if there are any questions.
Thanks, Sultan, for the very nice talk. Yeah, as Sultan said, any questions from the audience, also feel free to write them in the chat. Nilanjana raised her hand, so please, Nilanjana, ask your question.
Hi, Zoltan. Thank you for the talk.
I
just wanted to make you aware that way back in 2016, Jan Potra, Kambiz Ruze, and I had already studied hypothesis testing in the non-IID setting. And in fact, we also studied the second order asymptotics. And one of the examples was indeed the same that you're considering, that of quasi-free states of a fermionic lattice gas. So maybe I can send you the reference.
Was it? Yeah? May I ask you? Was it pure states or mixed states?
And we did not, in particular. It was mixed states. It was not pure states.
Yeah. For the mixed states, I would guess mostly it's still, but please send me your paper. It's obviously relevant. But for mixed states, I believe mostly what you will see is, of course, like in counter examples, they will be exponential separation, not super exponential, right?
Yeah, so we were not studying the question of super exponential discrimination, but what we did study was, you said that a non-IID situation wasn't studied before. We had studied it in explicit detail, including the second order asymptotics.
Yes.
Funnily enough, this quasi-free states in the car algebra of the fermionic lattice gas was one of our examples. Okay, so I'll just send it to you so that you can have a look.
Perfect. Thanks. Sorry,
okay.
I mean,
thank you very much.
Yes, of course, there were some studies already, and sorry that I missed your study, but
no problem.
There has been other by Funnes and others who also studied, but mixed states, and they haven't seen this super exponential one. That's what I wanted to.
Okay, thank you.
Thanks.
Thanks, Dana, for the question. Any other questions from the audience? Well, if not, then I can maybe ask a question myself. So do you think this is tight, this log n, or do you think it could be even higher?
That's actually a great question. Originally, I didn't think it's tight, and I wanted to make, and probably we still want to make numerical explorations in that. We didn't, I have to admit. But now when we will wrote up the proof more precisely, it seemed that now I believe that it's tighter, actually. But we should do numerics on this, at least, if not theorems.
I see.
Thanks for this question. Great question. I originally I thought, no, it cannot be e to the minus n log n, it should be e to the minus n squared, but no, I don't believe in one.
I see. Thanks. Okay, are there any other questions? So if not, then let's thank Gautam again for this very nice talk. And maybe I invite the next speaker to maybe try to share screen and just make sure everything works. We're all ready for the next. Okay, let's do. Maybe you want to make it full screen as well. Or do you want to be there like that?
Yes. Is it showing up as full screen?
Yes, it is. Perfect.
Okay, great. Thank you.
Thanks. Okay, I guess then we're all set up. So, but we still have 2 minutes, so maybe we can just have a 2-minute break while we wait for the next speaker. Okay, I think we can continue. So up next we have Sam Branson from Duke University, who is going to talk about the inevitability of knowing less than nothing. So please go ahead.
Thank you for the introduction. Yeah, so my presentation is going to be on the inevitability of knowing less than nothing, which is a reference to negative quantum conditional entropy. And I want to acknowledge my co-authors for this work, Gilad Kaur, Isabel Gung, and Mark Wilde. And in particular, I want to thank Mark Wilde for sharing some of his slides for this presentation. So the main goal of this talk, just to give an overview, is we first want to give an axiomatic formulation of quantum conditional entropy. Obviously, there have been multiple previous works that have investigated quantum conditional entropy, but most of them have focused on starting with a specific formula and then deriving properties of that formula. We wanted to show instead what we could find about the most general set of quantum conditional entropy functions based on an axiomatic approach. And we're going to show that every function satisfying the two axioms we propose must take on negative values for EPR states, which means that any plausible conditional entropy based on this axiomatic approach takes on negative values in quantum information. And this negativity of quantum conditional entropy is what we'll be referring to as knowing less than nothing. So to begin with, we'll start with what entropy is in the classical case, and then we'll move to classical conditional entropy, and then finally into the quantum case, and we'll end with our result of knowing less than nothing. So entropy in general is going to be the knowledge gained upon learning the outcome of a random experiment. So if you consider kind of just the simple example of rolling a dice, if you already know the dice outcome beforehand, if the dice is fixed, so just suppose if you know that every time the dice is rolled, you'll get a 3. You don't actually learn anything by performing the toss. You already know it beforehand because it's deterministic. And so the entropy is 0. But on the other hand, if you're rolling a dice that is uniformly random, so that all sides are equally likely, if the dice has d sides, then you'll learn log 2 d bits. So that's the maximally uncertain state and the roll that you learn the most from. And we can also imagine that if the successive tosses are independent, you would expect the entropy to also be additive. So the uncertainty of observing 2 different completely independent tosses is going to just be the uncertainty of individually observing the first toss plus the uncertainty of individually observing the second toss. And throughout this presentation, we're going to be considering only random variables that are finite. So we won't be addressing the infinite case at all. Now we can begin with 2 basic axioms for entropy. So an entropy function h is a function that's not equal to the 0 function, because otherwise we could have a trivial function. It's an uncertainty measure, which we'll define more in the next slide. And it's also additive for product distributions. So the product distribution corresponds to the case of 2 independent variables. So this is just the additivity of independent results. And the reference for this is a work by Gore and Tom Miefel. So what an uncertainty is. So we noted that the entropy function is non-decreasing under mixing operations, where a mixing operation is going to be a random relabeling of values. And you would expect that if you're performing random processes or random relabelings, the entropy or uncertainty, the uncertainty cannot decrease. So mathematically, a mixing operation means that with some probability qi, you'll perform a permutation pi. And the mixing operations are going to preserve the uniform distribution. So if you have the uniform distribution and you permute it, you're going to get the uniform distribution back. And intuitively, one way to understand this is that the uniform distribution is the most uncertain state. So you would expect that an operation which cannot decrease entropy must also must map the maximally uncertain state to itself. And so mixing operations must then preserve the uniform distribution and map it to itself as its entropy non-decreasing. So we can then define the function f to be an uncertainty measure for a probability distribution p if it does not decrease under the action of a mixing operation, and if it's invariant under embeddings. And what the second property means is simply that if you add an extra fixed result, if you kind of embed your observation in a larger space where the remainder of the space is constant, that your uncertainty doesn't change. So if we go back to the rather simple example of rolling a dice, if you now suppose that you're not only observing the outcome of the dice, but you're also observing whether the table that you roll the dice on is right side up or upside down, well, assuming normal situations where the table is always going to be right side up, your uncertainty will be unchanged there. It will just reduce to the uncertainty of the dice roll, because that's where the actual observation, non-trivial observation is. So what are the consequences of these axioms? The first consequence is that H is non-negative for all probability distributions and is equal to 0 for degenerate distributions or deterministic distributions. And H is going to be maximal for the uniform distribution of size D. Among all distributions of size D, the uniform distribution is going to be the maximally uncertain one. And as kind of a standard convention, if we normalize H so that the uncertainty of the maximally uncertain binary distribution is 1, then the entropy of the maximally uncertain d-dimensional distribution is going to be log 2 of D. We can now move into what conditional entropy is. So conditional entropy is going to refer to, it's related to the knowledge that we gain of outcome X, given that the value of Y has already been observed. So if X and Y are two random variables, the conditional entropy of X given Y is how uncertain X is, given that you have knowledge of Y. And if X and Y are independent, you can imagine that knowing Y doesn't tell you anything about X because they're independent. And so in this case, there will be no difference between entropy and conditional entropy. But in general, if X and Y are not independent, your knowledge of Y might inform your knowledge of X. And so your knowledge of Y might decrease your uncertainty of X. And so conditional entropy of X given Y cannot be greater than the entropy of X. And like the previous case, we would expect this to also be additive for independent trials. So if X1 and Y1 are independent of X2 and Y2, the conditional entropy will simply be the sum of the independent conditional entropies. And this leads to two basic axioms for conditional entropy in the classical case. So our conditional entropy function H is again going to be a function that's non-zero and or not equal to the zero function, and is a conditional uncertainty measure, which we can define analogously to the previous case in terms of conditional mixing operations. And it's also going to be additive for product distributions. So additive for independent cases. So we can now define a mixing operation. We know that previously the mixing operation preserved the uniform distribution. So it would map the maximally uncertain state to the maximally uncertain state. Now in this case where we're working with bivariate distributions, one sort of naive guess for what the bivariate distribution of maximal conditional uncertainty is would be simply the uniform distribution on X and Y. So which can also be written as a tensor product of the uniform distribution on X with the uniform distribution on Y. However, we know that this might actually not be the most general way to write a maximally maximal conditionally uncertain distribution. We know that after all, conditional uncertainty refers to your uncertainty of X, given your knowledge of Y. So as long as X is maximally uncertain, it's the uniform distribution. And as long as Y is independent of X and not giving you any additional information, you should have maximal conditional uncertainty. And so we can show that actually there could be many other distributions that also achieve maximal conditional uncertainty. So really, as long as Y is an arbitrary distribution that's independent of X, and X is a uniform distribution, we have maximal conditional uncertainty. And so that leads us to justify having this set here as our set of maximal conditional uncertainty distributions. And then we can define our conditional mixing operations to be operations which preserve this set. So a channel M is going to be a conditional mixing operation if for any distribution U tensor Q, which has maximal uncertainty, you're mapped to another distribution that also has maximal uncertainty of U tensor R, so where there's some distribution R satisfying this. So again, conditional mixing operations preserve the set of bivariate distributions of maximal conditional uncertainty. And a function F is going to be then a conditional uncertainty measure for a bivariate probability distribution if it doesn't decrease under the action of a conditional mixing operation, and if it's invariant under local embedding of X, similarly to the previous case. And so the consequences of these axioms are that H is non-negative for all bivariate probability distributions. So any function H will also reduce to an entropy for product distributions. So if X and Y are independent, the conditional entropy is going to just reduce to the entropy of X. So H of P here. And H will be maximal for uniform distributions of size D or for the maximally conditional uncertainty distributions of size D. And again, if we normalize this, then we find that the entropy of the maximally uncertain conditional distributions is going to again be log 2D. So having gone through the classical case, we can now move towards the quantum case and discuss what quantum entropy is. So inspired by the classical case, we want to use an axiomatic approach here. And we're going to have two axioms that are directly analogous to the classical case. The first one is that H is an uncertainty measure. And the second one is additivity. So in this case, if you have a tensor product quantum state, your entropy of that tensor product quantum state should be the entropy of the sum of the entropies of the individual states. So what is a quantum mixing operation? What is our quantum uncertainty measure? Just as in the classical case, we defined a mixing operation to be one that preserved the uniform state. We can say that channel M is a quantum mixing operation if it's a quantum channel that preserves the uniform state. And our uncertainty measure then will be that a function f is an uncertainty measure for quantum state rho if it doesn't decrease under the action of a quantum mixing operation, and if it's invariant under embeddings. So H is going to be non-negative for all quantum states, and we can also show that H will be equal to 0 for pure states. H will also be maximal for the uniform state of dimension D, again among under all quantum states with dimension D. And if we normalize H, we again find that the maximal entropy is log 2D. We finally introduce the basic axioms for conditional entropy. So a conditional entropy function, H is going to be a function that's not equal to the 0 function, and that will be a conditional uncertainty measure, and that will be additive for product states. So again, additivity for independent states. We can now define our quantum conditional mixing operations. So we know that in the classical case, our conditional mixing operations would preserve the set of maximally uncertain bivariate distributions, which were of the form U tensor Q for an arbitrary distribution, classical distribution Q. So in the quantum case, we are going to say that a channel M is a conditional mixing operation if for any state sigma B, there exists a state omega such that the channel M acting on U tensor sigma will give you U tensor omega. So we're preserving the set of maximally conditionally uncertain quantum states of the form U tensor sigma, where now sigma is just an arbitrary quantum state. So conditional mixing operations will preserve the set of states of maximal conditional uncertainty. And we can define the function f to be a conditional uncertainty measure for a bipartite state rho if it doesn't decrease under the action of a conditional mixing operation. So it doesn't decrease under the action of quantum channel M, if M is a mixing operation, and that it's invariant under local embedding of A. And in the quantum case, we can represent this local embedding as performing an isometry channel. So UA corresponds to an isometry. And the consequences of these axioms is, first of all, that H is going to be non-negative for all separable unentangled states. But our key result is that H can be negative for some entangled states. And this has operational applications to, for example, the quantum merging protocol. And we'll show in the next couple slides that H is negative for the EPR state. So what's sometimes called the maximally entangled state. We can also show that, again, H reduces to just the standard quantum entropy for product states. So reduces to H rho A. And H is going to be maximal for the set of maximally uncertain quantum states. So, and specifically the set of quantum states of the form UA tensor sigma, where sigma is an arbitrary quantum state in system B. So in order to prove that we always obtain negative conditional entropy for any quantum conditional entropy function that just satisfies these two intuitive axioms, I'll first define a channel that we're going to use in the simple proof on the next slide. So we can consider a channel, a quantum channel that goes from A tilde, A and B to A prime, where we suppose that this channel first discards system A tilde. And then we can suppose that the channel next performs a quantum measurement, where the first outcome of the quantum measurement corresponds to the EPR state. And the second one is going to just then, of course, be the identity minus the EPR state. If we observe the first outcome corresponding to the EPR state, we'll prepare a pure state afterwards. And if we observe the second outcome, we'll prepare the orthogonal state. And we can show that this is going to be a conditional mixing operation. So then the proof of negative conditional entropy is as follows. You can take the conditional entropy of the EPR state and you can add log 2 of the dimension of A. However, we know that the maximally uncertain state on system A tilde, if A tilde and A have the same dimensions, which we can suppose here, that this will simply be log 2 of the dimensions of A. So we can replace the second term with the entropy of the maximum uncertain state on A tilde. And we can then recombine these in the second line. Now, because we identified in the previous slide that the channel is a conditional mixing operation, the entropy of this product state of the EPR state tensored with the maximum uncertain state on A tilde cannot decrease under this conditional mixing operation. And so we obtain the inequality here. However, since our channel involves measuring the involves a measurement that corresponds to the EPR state or its complement, we're always going to obtain the first outcome. And so the pure state, state 1, will always be prepared here, and the entropy of a pure state will be 0. So then upon rearranging, we find that the conditional entropy is not only negative, but also we can identify its value as negative log 2 of the dimension of A. And so in summary, we've formulated a simple axiomatic approach to quantum conditional entropy based on 2 sensible and simple axioms. We've used these axioms in a simple proof to conclude that quantum conditional entropy is negative for certain entangled states, and we've specifically shown that for the case of the EPR state. One of our open questions is we've identified a lower bound on the conditional entropy and have shown that that's achieved for the EPR state. We would like to also show that the conditional max entropy is an upper bound. So that's an area for potential future work as well. That concludes the presentation that I prepared. Happy to answer any questions.
Thanks a lot for the very nice presentation. Do we have any questions from the audience? We have a lot of time, so please don't shout. Well, maybe I can start with one. Is it known how to characterize these conditional mixing channels? Do they admit some nice characterization, or are there nice criteria or that one can use to show that a channel satisfies this?
I'm so sorry, my audio is having a bit of trouble. Would you mind repeating?
Oh, maybe. Yeah, if these conditional mixing channels admit some nice characterization. Like, because for the mixing channels, it was just being unital, right? Is there a similar simple criteria to show that one of those, that a channel is conditional mixing? Was that question clear now?
Yes, thank you. That's a good question. I believe that Dr. Gore, one of the co-authors, actually found this week that the for the classical case, that the conditional mixing channels relate to the set of conditional doubly stochastic maps. So maps where you're performing essentially a sum over J of individual mixing channels of DJ tensor Fj on the different systems.
I see. And but quantumly, nothing is known, or
I think we recently showed that the maps which are conditional mixing correspond to that set of conditional doubly stochastic maps.
Okay. Okay, I see that Niranjana raised her hand, so please, Niranjana, go ahead.
Yes,
Niranjana. I think you're muted. Or
Hi there.
no.
Yeah. Thanks, Sam, for this nice talk. you know the Renyi entropy, right? So the classical Renyi entropy, and there are various ways of generalizing it to a conditional Renyi entropy. And we had looked into this question, and there is one form of Renyi entropy due to Arimoto, or the Arimoto Renyi entropy. And if one wants to look at these various conditional entropies and wonder which one is the correct one, so which leads us to a similar axiomatic way of looking at things. And then we found, according to us, what we found, what we thought was most natural was one of them to take, for example, hx given y to be less than equal to hx. Why? Because if you know, get rid of the uncertainty of the one random variable, which is the y, then you should be having less uncertainty. So hx given y less than equal to hx. And the other one was a lower bound that hx given by cannot be too less. It cannot be, so it should be greater than equal to hx minus the logarithm of the dimension of the y alphabet. You see, these are two very natural axioms. So how do these compare with, so there is a reduction in uncertainty if you know one random variable, but the reduction cannot be more than the knowledge you gain about the other random variable. So how do these two, which I consider quite natural axioms, compare with your axioms? Let's just stick to the classical case.
Yes, I'd be very interested to read your paper. It sounds very closely related. And may I ask how you, it certainly makes sense that you'd want the conditional entropy hx given y to be less than h of x. May I ask how you specifically came up with the second axiom, kind of bounding the maximal reduction in conditional entropy that you could have?
Yeah. What do? We look at Shannon entropy. Yeah, Shannon entropy satisfies that, and it is also intuitively clear because the reduction in uncertainty cannot be. Why is your uncertainty being reduced? It's because you're gaining knowledge, right, or information. So the reduction in uncertainty cannot be more than the amount of information you gain, and the maximum amount of information you can gain is the logarithm of the alphabet size, right? But don't worry, I just wanted to throw this out there and we can discuss this later on.
And so then the, did you find sort of similar, I guess when you're asking how it compares.
With your basic axioms.
I guess, yeah. So the, sorry, there's quite a few slides. The consequences that we find are here. Were you able to find, I guess, were your consequences identical or something?
No, it was not a question of consequences.
Oh, okay.
These two criterion, which we can almost look at as axioms, yes. It isolates the Arimoto-Renyi as the right, quote unquote, right way of defining the conditional entropy arising from the Renyi entropy. Yeah, so those were the axioms which isolates the Arimoto-Renyi compared to many other possible definitions of conditional Renyi. So that, but let's take this offline and we can talk about this. Yeah.
Yeah.
Thanks, Nilanjana. Any other questions? Well, then let's thank Sam again, and let's take a break for the next talk as it's true.
We have a serious problem. So the final speaker is should be Mario Berta, but he does not stay here. So initially, somehow, so we have some trouble with him. So because in this Beyond IID, we ask the time prevalence. So, however, his paper, this paper does not reply that time prevalence.
Yes. He just entered the room. He entered the room. He's here.
Doro.
Mario. He just
With
entered.
Doro. Why you know? Okay. Now here. Okay.
Hello.
Okay. So now you can make a presentation.
Yes. Thank you. Sorry, yeah, I'm late. It's very early here, so I just logged in. Perfect. Let me find the slides. Yes.
So Daniel, please take role of session here. Sorry.
No worries.
Hey guys, let me go. Close a few things. Okay. Yes. Can I share my screen? Is that possible? Let me see.
Yes. So are you having trouble sharing your screen?
No. I'm just setting up. Sorry, I still have 3 minutes, right?
No.
Or 2 minutes.
No. Yeah, no. We're just wondering if there's something we need to do or no. It's
No,
perfectly
let's see. I hope not. Microsoft PowerPoint here. That's the presentation. Yes. Which screen do you guys see now?
On a gap. So there's like a slide on a gap in the proof. So it looks good to me.
Looks good.
Maybe
Now you see next slide.
No, I don't. Oh, now I do.
Okay, just a bit delayed, but otherwise it works.
Okay, this is okay.
Yeah,
Is it okay?
it works. Yeah, it should be working. Yes.
Okay, let me quickly get something to drink and then I'll be right back. Is that okay?
Sure.
1 minute. 1 minute.
Yeah.
Okay. I would be ready then. Just let me know.
Yeah, then maybe we can already start. So yeah, the last speaker of the session is Roberta from the AWS Center for Quantum Computing in Pasadena, where it's currently 5 a.m. if I'm not mistaken. So thank you for joining us so early. And I guess also from Imperial College London. So he's going to talk about on a gap in the proof of the generalized quantum science lemma and its consequences for the reversibility of quantum resources. So Mario, please, the stage is yours.
Thanks a lot, Daniel. Yeah, sorry that I joined a bit late. So how long is the talk actually? Is it like 25 minutes or something like that?
Yes, exactly. 25 minutes plus 5 minutes of questions. I'll let you know in the chat when you have 5 minutes left.
Perfect. Yes. Good. Yes. Yeah. So this is about this new preprint that we put out here. This is the second paper on this slide. However, I decided to also mix in a little bit of this previous work, this on composite hypothesis testing, because this first work actually gives us means to prove generalized Stein's lemma, where the second paper well, it uses other methods as well, but it also points out some problems with previous work. Anyway, let's just get started. So the way I was thinking of doing this talk is to first just talk a little bit about hypothesis testing in general. And I think I can go through this quite fast because there's a specialized audience here. Then same thing about resource theory, just the very basics. And then the question if resource theories become asymptotic reversible, this is connected deeply to hypothesis testing. So then the third point of the talk will connect these two things. And then I think I won't have a lot of time to talk about possible proof techniques, but let's see when we get to it. Good. Okay. So what is hypothesis testing? Quantum hypothesis testing. Well, the simplest setting is that we have two sequences of states. Let's say rho n and sigma n, and then we would like to discriminate which of the two we get. Okay, we're told we get either rho n or sigma n, and then we want to apply this two outcome PVM to find out which one we actually got. And of course, then we can make two types of error, this type 1 and type 2 error. So we can either mistakenly identify rho n as sigma n or sigma n as rho n. And of course, the very simplest setting here is if this sequences of states, rho n is just a tensor product sequence, rho tensor n, and the same for sigma. And if we look at this task, we can look at different ways of minimizing this type 1 and type 2 errors. So the one setting is the symmetric setting, where we just take the sum of the two errors, or we weight them with 1/2. We want to find a measurement that minimizes this error. And then asymptotically, this is the so-called quantum Chernoff bound. So we can define this exponent. Okay, so it's easy to see that for the optimal measurement, this error decays exponentially, and then we can ask with what exact exponent does it decay, and then there's this nice closed or nearly a closed form solution in terms of this Petz-Renyi divergences here on the right-hand side, right? So on the left-hand side here, you have the definition of the exponent you want to quantify, and on the right-hand side, you have this nice neat characterization. So this is an example of a result in quantum hypothesis testing. Now, for this talk, I don't want to talk about the symmetric, but about the asymmetric a setting where we don't treat the two errors equally, but we have this alpha, an error that we want to keep smaller than epsilon, and then we want to see how fast the beta n error decays. And again, it's easy to see that this error decays exponentially, and we can ask with what exponent does it do so asymptotically, and then what comes out is the so-called quantum Stein's lemma, and we get this quantum relative entropy as the answer here for this asymmetric setting. Good. So these are very fundamental results in quantum information theory. They're useful for many things. Now, what is relevant for research here is actually an extension of that, which is so-called composite hypothesis testing. So here we don't know that we're given this sequence rho n or sigma n, but we only know that we're given some rho, and then the rho tensor n version from some set T, and we're given some sigma from some set S. And then we can ask the same questions about symmetric and asymmetric quantum hypothesis testing and the asymptotic optimal error rates. So the point here is, of course, that we have to design a measurement that is good to distinguish all rhos and all sigmas from each other, kind of with the same measurement simultaneously. Good, yeah. So in this in the setting where we again look at the tensor product sources, right? So this alpha n error here, we now have the thing that's to be smaller than epsilon for every rho in this set T, and the same thing for the beta n error. We need to be small for every sigma in the set S, and yeah, we want to find the optimal two outcome PVM. And the thought after characterization is the same, and we want to look at this asymptotic error exponents. And in particular, yeah, I want to work with this asymmetric setting. Now one could equally well look at the symmetric setting. Good. So now let's quickly look at the classical setting. So if rho and sigma, if they pairwise commute, which lets us go into the common eigenbasis, and so we just have the classical setting. I'm not sure if this is the original reference, by the way. If anyone knows an earlier reference, please let me know. But what happens in the classical case here is very beautiful. Namely, you just get that this composite error exponent is given by the infimum versus the minimum over all the individual exponents. So you just can use the relative entropy formula. So it is just the classical version of it in terms of the Kullback-Leibler divergence, and minimize it over all the inputs. Well, okay, so here it's P and Q because it's classical, so you can look at probability distribution. And you can see, of course, you cannot have an error smaller than that, right? Because it could be any rho or sigma that you're actually given. So this error exponent is kind of, you immediately get a converse from the standard hypothesis testing setting. But the point is, you can actually design a measurement that also achieves this exponent. Now, next step, of course, is to ask, okay, can we do the same quantumly, or do things change? And yeah, there have been many like partial results on these questions. I would say they might again be missing some references. Please let me know. But this first paper that I listed at the beginning of this talk derives the following, let's say, at least as long as the sets S and T are convex and channel formula. So one can write this asymptotic composite error exponent in terms of this like regularized formula here. Okay, so we have the relative entropy on the right-hand side. The first element is just the rho tensor n, as we might expect it, but the second element is not just a sigma tensor n. I mean, if it would be just a sigma tensor n, the relative entropy is additive on the tensor product states, right? So we could simplify this formula to the nice classical formula we saw before, namely what we have on the right-hand side here. However, we have to look at like convex combinations of sigmas, where all the sigmas are just in the set S. And as you can see, at least a priori, this formula, this regularized formula we find here, it's not necessarily the same as this, people call it single letter formula here on the right-hand side that became the classical setting. And indeed, we can construct examples, so we can give like convex sets rho and sigma, for which these two sides are not the same. So for which we really need this multi-letter formula. And this actually, one can see, I guess, an underlying technical reason why this is not true is because, contrary to the classical setting, we cannot lower bound this relative entropy distance between rho tensor n and these convex combinations as n times just the relative entropy distance between rho and sigma, where we minimize over sigma. And okay, so for n equal 1, this might not hold, but classically this holds kind of approximately for large n, and then in the asymptotic limit it holds exactly. And this is what allows this like simple and clear quantification in the classical case. But quantumly, yeah, there are actually counterexamples to this entropy inequality. Good, and I okay, maybe let me make two comments here. So one is that Milan, he recently found that this these multi-letter formats are also needed in the classical case as soon as we go to continuous alphabets. So if the if the underlying spaces are continuous, this is actually this single letter quantification already is wrong classically. So this is not necessarily only a quantum effect. So that's the first comment. The second comment is that if we choose nice sets S and T for the sets of rhos and sigmas, then in many examples we anyway have a single letter quantification. However, this is not like a general off-the-shelf result, but we have to kind of manually prove it every time for like nice setting. Good. So this is kind of the landscape around hypothesis testing that I wanted to introduce. Are there any questions so far?
Can I ask a question, Mario?
Yes, Nirajan, hi.
Hi there. So nice means what sort of nice?
Well,
Can you give one example? Yeah.
When this is nice, I think there is this resource theory of coherence or something like that. It then, so I think you fix rho and then the optimization in the second argument becomes thing null letter. Yeah, it's basically just whenever this entropy inequality here at the bottom, when one can show something like that. But I don't, this is, yeah, maybe this is my problem, maybe this is a general problem about this question. I don't have a good handle on like what it means, like technically to be nice. I mean, in some sense, like as classical as possible. Yeah.
Okay, thanks.
Thanks for the question. Yeah. Okay, so then let me switch gears for a second and talk very briefly about the resource series. I think most people here probably know about this in and out and better than I do. But yeah, actually, let me just choose this resource series of entanglement, even though we can make similar considerations for general resource series under some suitable axiom sets. Okay, so in the resource series of entanglement, of course, free states are separable states. So this is just the convex hull of product states. So we're given this like bipartite Hilbert space structure. And then the separabilities with respect to this cut into A and B. And then all other states that are not separable, that are not in the convex hull of product states, are called entangled. And that's what it means to be resourceful in this theory. And then there are all these like a central object in resource series. So actually the resource series of entanglement has this nice unit, the E-bit, okay, which is just like a maximal entangled state between two qubits. So this is kind of the unit, yeah, or the maximum entangled states, maximum resourceful states. And then we have to define further things. So one is like what type of entanglement measure do we want to use? So that measures like not only if the state is resourceful or not, but also like how resourceful it is. And what we're going to use for most of the remainder of the talk is the so-called global resource robustness. So here you start with the state rho AB, and then you ask how entangled is it? And this is now measured by how much of another state, sigma AB, you have to add, such that the resulting state becomes separable. Okay, and then of course, okay, it's just renormalized again. Okay, so the question is how much of some other state you need to add such that the resulting state becomes entangled. And the more you have to add, the more entangled the state is. That's kind of the intuition of this measure. Good, and then the last ingredient of the resource theory here is what are the free operations if you go from one state rho to another state omega. And of course, you could choose different mathematical objects. Here you can look at this like local operation and classical communication, or you could look at positive partial transfers type of transformations. But since we're going to be interested in the reversibility or the potential reversibility of the resource theory, it makes sense to look at, in some sense, the largest possible set of operations, and these are the so-called delta non-entangling operations. So this just means you allow any quantum channel, any quantum completely positive state specific map from some bipartite input space AB to bipartite output space A prime B prime, such that if you apply this map, you only create negligible amounts of entanglement. Okay, you do potentially create a bit delta, and this is, well, on the one hand, this is a mathematical convenience. On the other hand, you might say this is like even physically motivated, because you never fully control what you're doing. So maybe it makes sense to allow for like tiny bits of entanglement. But this is, in some sense, the largest set of operations that makes sense to consider. Good, and then we can ask about how much entanglement can one distill. And here, okay, so this is a general formula. It's not so important. The point is just if I start with the state rho tensor n here, then the question is if I use this optimal delta non-entangling map, how many EBITs can I distill asymptotically? Okay, so this is the distillable entanglement. And the same way I can define the entanglement cost under this delta non-entangling operation. So here it's just the opposite. So I start with many EBITs, and then the question is if I use the optimal map lambda, how many copies of rho tensor n can I get? Okay, so this is like one time I'm given the state rho, I want to distill entanglement. One time I'm given these EBITs, and the question is how many of these, what is the cost of these to make the state rho? And they're always like asymptotically. Or then more generally, I can look at transformation rates, right? I can ask, okay, at what rate can I go from my state rho to another state sigma? Again, asymptotically, and always under this delta non-entangling operation. Again, so the exact formulas here are not so important, but I think, yeah, just the intuition of the task behind it. Okay, let's see. Yes, and so now the question is does this resource theory become asymptotically irreversible? That means if I go from a state rho to a state omega, okay, at the asymptotically optimal rate, and then I go again back to rho, do I not lose anything as a net cost? Or I mean, resource theory of entanglement has this maximally entangled state, is EBIT. So actually the question here becomes equivalent, is the distillable entanglement the same as the entanglement cost under these delta non-entangling operations? So these are two equivalent formulations of the same problem, and yeah, is that true? Okay, so now let's look quickly on what is actually known about these quantities, the distillable entanglement and the entanglement cost of general states. And the entanglement cost actually has this characterization in terms of this so-called smooth max relative entropy. I don't want to introduce the formal definition, but one way of writing the entanglement cost is as this regularized relative entropy distance formula. Okay, so you look at the relative entropy between rho tensor n, and then the next state, sigma n, where sigma n is in the state S, and S are the separable states, but of course now on n copies. So these states are separable between the A copies of n and the B copies of B. And here, just as a side comment, this regularized formula can in general not be singularized. So again, we have to look at this like n copy limit. Good, so this is what's known about the entanglement cost. Now, the distillable entanglement, we have a formula for the distillable entanglement, which connects resource series now to quantum hypothesis testing. And we can write this asymptotic distillable entanglement, we can write it as a hypothesis testing problem, and the composite hypothesis testing problem at that. So we look at this asymmetric error exponent, and we're the first argument, we have the rho tensor n. So this is the fixed state rho that we are interested find the distillable entanglement of. And then in the second argument here, the set Sn. So these are again the separable states. So we need to find a hypothesis test that distinguishes the rho tensor n and all separable states on n copies. Okay, and now if we want to know if the entanglement cost and the distillable entanglement become the same, one way of showing that would be that this hypothesis test quantity, hypothesis test problem, does it allow to be written, I mean, asymptotic quantification of this asymmetric error exponent, again, in terms of this regularized relative entropy formula, right? Because this is how the entanglement cost could be written. So if we could show that this entanglement permits the same formula in terms of this relative entropy distance, then we would be done. Then we would know that the entanglement cost and the distillable entanglement are the same, and that the theory of the resource here of entanglement under this delta non-entangling operations becomes asymptotically reversible. Good. Any questions so far about this? Okay. Good. Yeah. Yes, Marcel.
I think in my textbook, I already discussed this one. So in this case, we should choose somehow please. No. At least in the case of pure state case, we discussed that problem.
Pure states, yes.
No. In order to drive the combat start, this quantity is bounded by a relative entropy of entanglement. So in order to prove that argument, we should use this one. So I discussed that method to discuss the combat.
Sorry, I'm not sure I understood you. You discussed that?
In order to discuss the combat part of the decrease of entanglement.
Yes.
So in that case, I discussed that method, I think.
Okay. In a talk, so maybe I can look at the
Okay.
the video. Yeah, no, that'll be good. Yeah. Thank you. Yes. So here, okay. So here, this is specifically for this. Yeah, this delta and non-entangling operations. But okay. So yeah. So this is the question here that one might ask. And okay. So to get a converse is simple. So I don't really want to talk about it that much. But basically, one can show that this hypothesis testing a problem, this error exponent is upper bounded by this relative entropy formula. So this follows relatively easily. But now what we found is that the achievability direction here actually remains open. So that would be the inequality in the other direction. And now you might say, okay, but now in the first part of my talk, I talked about this like composite hypothesis testing. Now we just have to look at this composite hypothesis testing problem here. Why don't we use the results from before? So let's see. So the rho is just a fixed state here. So that fits perfectly into the setting from before. However, the set of separable states here is unfortunately not of this form that I talked about in the first part of my talk. And the reason is, even though these states are separable between all the A's and all the B's together, they might be entangled across the different A's and the different B's. Okay, so that's why this is not an IID setting. And we can just use some of these results I presented before. Nevertheless, it might still be that we have a similar type of regularized relative entropy of entanglement formula that quantifies this hypothesis testing problem. Good. So I think I won't have much time to talk about proof techniques, but let me say that a couple of things actually can be shown, which maybe are not very satisfying, but nevertheless. So if indeed we change the research theory of entanglement bit, and call it pseudo-entanglement theory, such that we actually do have all this separability, not only between all the A's and all the B's together, but also between all the individual A's and individual B's. So if we only look at those free states, then indeed we can show that we get this regularized relative entropy of entanglement formula. But okay, we get this nice formula, but the resource theory underlying it changes, of course. Okay. And then we can play this a little further if we want. Namely, we can say, okay, we can just take k's of the A's together and k's of the B's together, and then look at that resulting resource theory. And indeed, we can also do that. Okay, so we can also look at these groups of k's and then make k larger and larger, and then we actually kind of intuitively would go back to the original entanglement theory, and then we get the full, on the right hand side here, we get this full relative entropy of entanglement formula. Whereas before, okay, so I didn't really emphasize that, but before we had this set S bar, right? the set S bar was set of separable states that were also separable between all the A's and the B's. So in some sense, we had a clean resource here on the left-hand side, but the wrong one, and therefore also the wrong regularized relative entropy of entanglement formula. Whereas here in this, if we take these blocks first and let the size of the blocks become large, we do get the right formula here on the right-hand side. However, here on the left-hand side, we have a problem because we cannot just exchange these limits here. The limits, okay, going to infinity, epsilon to 0, and going to infinity, we have to have them in this order. And because of that, we can't really connect the left-hand side to the resource area of entanglement. Okay, it's like a bit of a weird problem, but uniform convergence. But this is how it shows up if we go this approach. And so let me say that, yeah, this question about the achievability is a question that remains open as far as I know. And okay, in terms of proof techniques, yeah, we need to design these universal hypothesis tests. And from how I see the literature or the landscape, there are basically three approaches. So one goes through this like ordinary inequality and uses this Petz Renyi divergences. Another possible proof approach uses the so-called like measured divergences. So this is kind of a relative entropy distance where you first measure and then just apply like classical measures. Or the third possible approach might go through this like smooth max relative entropy, where we kind of try to connect this hypothesis testing quantity with the smooth max relative entropy. And unfortunately, with all of the three approaches, we run into some bottlenecks, if you want. And okay, I could tell you what the exact technical problems become in each of these settings, but I think I'm pretty much out of time. But generally, it's always a type of like a uniform convergence question, like I had from this previous slide here, where I can't interchange limits. I have to take the limits in a certain order, but I would, like them have in a different order. And this is where we kind of get stuck. Yes, I can share my slides also afterwards, but I think I might just straight jump to the conclusions now. And yeah, sorry, these slides from a longer talk. Let's just take a second to get there. I mean, yeah, it's really, one always gets kind of in the same problem. Yeah, let me maybe just say here also, I think there are quite a few other similar open problems in the literature that have a very similar flavor in terms of what the technical bottleneck is at the moment. So I think if one could solve one of these problems, one could also show all the others. But okay, it's just some technical intuition. Yeah, conclusion here, yes. So again, as far as I know, this distillable entanglement and entanglement cost under this delta non-entangling operations, we do not know if they're the same. However, one way I could show this, it's actually even only if way, is if this hypothesis testing a quantity can be quantified as this regularized relative entropy of entanglement distance. A couple of comments again. I think we have to be careful because this is a non-IID problem. So even if we go to like classical settings, now a non-IID problem, it's not immediately clear if we have such a relative entropy formula. And then of course, for certain resource series, again, this resource series of coherence comes to mind, and one can show this conjecture if you want, but one basically has to show this manually every time. So for some nice resource series this works, but in general, like for the resource series entanglement, I don't think we know. And also let me say that in every case that we do know that this conjecture holds, the right-hand side becomes single letter. So I'm not aware of any setting where the right-hand side stays multi-letter, like here necessarily. But we can resolve this conjecture. And so my guess actually is that this reversibility does not hold in general. And there has been this recent work by Ludovico and Bartosz, and I should probably stop here But basically, what their work shows is that if you replace this global resource robustness as the entanglement measure with a different entanglement measure, just the resource robustness, so this R bar, and the difference here is just that you don't ask how much of another state sigma you have to add, such that the state becomes separable. Here you ask how much of another separable state you have to add, okay, such that the resulting state becomes separable. So if you use this slightly different entanglement measure, so you and correspondingly the set of free operations, and then one can actually show that the corresponding resource theory of entanglement becomes not reversible. So this conjecture about the state of entanglement is wrong. So in some sense, I think if the theory would be nice, this theory shouldn't depend on the exact choice of your entanglement measure. But it seems that it does. So even if reversibility holds, it will only hold for like some very specific entanglement measure. So that might not be super satisfying, but yeah, this is what stays open. Okay, so let me go back. Maybe, yeah, this is the question. Okay, thanks. I'm going to finish here. Thanks a lot.
Thank you very much. Sorry, so Daniel was chair of this session, but unfortunately he have to leave because at that time he take a chair of session on this session in airport. So maybe he have to catch his flight. So then he already left. So instead of him, so I have to take role of session chair. And
okay.
Sorry, my previous comment is somehow misleading, so I completely misunderstand. So please ignore. So is there any comment or question? Question or comment? So I understand. So okay, so what is the problem? So previously, ED-ANA equal to EC-ANA. So that's Premier and Fernando's paper discusses that point. But now you find the gap because in order to prove that equality, you need to prove this convergence. But that convergence is still open. So now I could understand. So really, this is not trivial.
Yes, so sorry, yeah, exactly. So if I jumped to this slide 50 that I didn't show before, okay, there's a lot of formulas on here. But basically, if you look at the last line here, so what they claimed is that this information variance between rho tensor n and this sigma n, that it would decay exponentially or like nearly exponentially. But this is in their analysis basically what went wrong, and yeah, but I don't know how fast this. I mean, that would be one way of tackling this uniform convergence problem.
Also, the difficulty of this topic is following. Now that original problem is not exact distillation, not exact entanglement cost. This is approximate, a kind of approximate of the entanglement distillation and approximate of the entanglement cost. Not this one is different from usual constant distillation rate.
So here it was this delta non-entangling operations, yes, and
so could you back to that definition? So
yes,
not
yes.
hypothesis testing, original problem. So original problem.
Yes, sorry, I have to find the slide.
So now okay. Now next, yes. That's impression version. Yes. In that,
wait, no, one more. I think I just want here. So these are. Is that what you're referring to? These delta non-entangling operations here?
Yes.
So you just you.
Maybe next one is better, I think, because
okay.
yes, ENE, yes, this one. So ED-ANE and EC-ANE, so not ED and not EC. So what is the difference? Because you allow delta N. delta
Yes,
n.
there's
So
there's
if
there's a
delta
finite
n
delta
exact,
n, yes.
if delta n equal to exact 0, so in that case, this one becomes distillation
if
and cost.
Yes, if delta n is 0 just for every n, then we know that the entanglement cost and distillable entanglement are not the same.
Yes, so usually in the case of cost and distillation, we consider the case with delta n exactly equal to 0. But now you relax that condition, then you define this quantity. This one is ANE. What is the meaning of ANE? ANE is
I
asymptotically
guess maybe
non.
almost non-entangling. So let me also say that like Brandao and Plenio did all of that, right? Like just like that's was their idea was to allow for this delta n to be non-zero for every n, and then they thought they could show that under this relaxation, entanglement cost and entanglement rate was the same. They enlarged the set of operations because then they thought they could show that the theory becomes entanglement.
Asymptotically non-entangling operation. Asymptotically non-entanglement operation. So this is somehow a reaction of the our operation, the relaxation of our operation. So then Fernando and Martin consider that if we relax that condition for our operation, these two quantities may be same. But to prove this one, they assume that one. Okay. Please, Nirajala. So
Yeah, just a question, somewhat oblique question. So you see, with this non-entangling operations, yeah. So these we know are physically less meaningful in the entanglement case than the LOCC operations, right? Because like a swap, it is this is a non-local operation. So my question is to do with general resource theories. So in resource theories, you would replace this asymptotically non-entangling operations, if I understand correctly, by asymptotically non-resource generating operations, right?
Yes.
Yeah, and so do you have this scenario there too, that these for physical operations, or are they like this NE operations or delta NE operations, that they're mathematically well defined but could be quite removed from what one could physically do in that resource theory?
Yes, I mean, in this original framework of Brandao and Plenio, that was the case. They would just show this in this kind of like black box way. They would say you have a general resource series, you define this like general none or delta none resource generating maps, and then you could show the reversibility. However, if you look at specific resource series, then it might be that you can actually already get these reversibilities between distillability and cost for operations that are actually physical, right? Like here it's just proven like in this general way that you need to use these most general operations. But if you have a nice resource theory, it might be that, you know, it already becomes reversible under actually like physical operations. I mean, it depends on your resource theory, but then you have to kind of prove it by hand every time. You can't use this black box result. I mean, anyway, the black box result turned out to be not complete, so you can't use it anyway. But I mean, so basically the setting is just like we know by now that for composite quantum hypothesis testing, or even for classically composite hypothesis testing, we have to be careful and we have to kind of like look at the problem one by one. There's not like a general nice solution, and I think it's going to be the same as the reversibility of resource theories. It depends on the exact structure of the like free states and so on and so forth.
Thanks a lot.
Thank you.
okay, is there any other comment or question? Okay, now we want to close this session. Thank you very much.
Thank you, Masahito. Thanks a lot.
Can I just say something? On behalf of everybody attending Beyond IID, I would like to thank Masahito and all the other organizers for organizing this nice Beyond IID meet and keeping this tradition going. Thank you very much, Masahito.
Oh, thank you.
Thanks, everyone. Yes, definitely.
So, yes, in this Beyond IID, there is two organizing committee. One is by two Yu, he is a postdoc of SUSTEC. Another guy is Don Yang, he is a researcher of quantum issues in SUSTEC. So they take some role of the organizing committee. So thank you very much. So we will have a session chair and business meeting. So business meeting will start from 20 minutes later. So we have 20 minutes break. Later we have that discussion. So thank you very much.